this is the fifth day of our discussion on your PGDSC program, in which we have discussed, uh, s- I think, 8 units of your MCS-02 paper. That is a course title, that is your MCS-02. And in the beginning, we have discussed the different separation techniques, like your physical separation of filtration, distillation, fractional and distillation, and followed by the solvent extraction part 1 and solvent extraction part 2. Then in the preceding units, we have discussed the chromatography section, which is the modern tool for separating different components in a mixture or a compound. And under chromatography, we have discussed the basic chromatography principle, that in a chromatography method, two phases are there. One is the stationary phase, another is the mobile phase, and depending on the type of stationary and mobile phase, and also the mechanism which is involved in separating different components of a mixture, accordingly the name of the chromatography is made. So under this purview, we have discussed the first type chromatography, which is the planar chromatography, and this may be of two types, that is two-dimensional planar chromatography and three-dimensional. So under two-dimensional planar chromatography, we have discussed the paper chromatography as well as the thin layer chromatography, and under the three-dimensional planar chromatography, we have discussed the column chromatography. So in paper chromatography, we have a chromatography paper on which we have mark a reference line below, that is the lower part of that paper. It is about 2 centimeter from the baseline, and this line is treated as the reference line or the line of origin. On that line, we have put our sample and make it dry with the dryer, and after that, in a suitable solvent, we place the paper either in ascending or in hanging position. If it is just dropped inside a suitable solvent within a chromatogram, we may say it is a closed chamber. And gradually, what happens, the different components after interaction with the solvent, that is the mobile phase, the different components get separated, and this is based on your absorption phenomenon. Then different components are separated uh, by, that is known as the, with reference to their retention factor, right? Retention factor. The retention factor, it is all about the retention factor is all about the interaction between the component at the stationary phase. So where the interaction is strong, it is at the lower part, but the interaction is more, it is at the upper part. Okay, and it gets separated first. So in thin layer chromatography, what happens? If stainless steel or plastic, or that is the polymer, with different dimensions, a silica gel slurry or alumina slurry is made, and it is uh, uniformly it is spread over the TLC, and it is allowed to dry. And after that, the same way, the reference line is drawn, and the sample is dried, and in a suitable solvent, it is the chromatogram is run, and accordingly the preparation was made. So in the column chromatography, we have a column that is in the form of a cylindrical tube, where silica gel with different pore sizes are packed inside the column, with some cotton at the lower and upper end of the column. Then when the sample is uh, placed inside the column, then the mobile phase is run, that is the solvent phase, and according to that interaction or attachment or bond formation or adsorption or partition, the different components get separated according to their properties. And if in a liquid chromatography, if the stationary phase is solid, it is said to be liquid solid chromatography, and if it is a liquid, it is liquid chromatography. In liquid solid chromatography, the phenomenon is absorption, and in liquid chromatography, the phenomenon is partition. So this is all about liquid chromatography. Then we have discussed the gas chromatography. So similarly for gas, we have GSC and GLC. For GSC, that is gas solid chromatography, we have the solid phase acts as the stationary phase, and the gas acts as the mobile phase. In GLC, liquid acts as the stationary phase and gas acts as the mobile phase. So in GSC, that is gas solid chromatography, the phenomenon is adsorption, and in GLC, the phenomenon is partition. So when adsorption takes place, the retention factor is calculated. When partition mechanism takes place, the partition coefficient or your distribution coefficient was calculated. So on the basis of this, our high performance liquid chromatography or gas chromatography mass spectrometry type advanced tools are manufactured, or it is nowadays these instruments are very frequently used for separation. And in the spacecrafts that are sent to Moon or Mars, generally the GCMS uh, instrument is sent with the spacecraft to uh, trace the rare elements that are present in their atmosphere, as well as the mass of that element, which is calculated by the mass spectrometer. And today the first unit which we will discuss, that is the unit 9, that is ion exchange chromatography. And in the next part we will discuss the size exclusion chromatography. So I have a PPT that is ready for you, that it is the ion exchange chromatography. So in this chromatography, it may be defined as the reversible exchange of ions. Is it visible, students, clearly, or any problem? Is it visible?
No, sir,
No,
not
sir.
visible.
Or not visible? Wait. Now,
Yes, sir.
okay, thank you. So ion exchange chromatography, this is all about exchange of ions in a chromatography, that may be cation or anion. So we have two type of exchangers, cation exchanger and anion exchanger. Okay. So we will discuss in the latter part. So this chromatography may be defined as the reversible exchange of ions in the solution, with ions electrostatically bonds to some sort of insoluble matrix or a stationary phase. So the stationary phase applied here is the insoluble matrix or insoluble solute we have, on which the ions are electrostatically bound. This technique is extremely useful in the separation of charged compounds like protein differing by only one charged amino acid. In ion exchange chromatography technique, one can choose whether to bind the substance of interest and allow the contamination to pass through the column, and vice versa. The technique has been developing since 19th century, which was firstly used for purifying drinking water. And this technique is very commonly used in large scale demineralized water plants. Okay, ion exchange chromatography is a distinct principle of chromatography performed in the column. So big size columns are there made up of polymer or plastic, and the ion exchanger, that is the cation exchanger and anion exchanger are there, and accordingly the water gets demineralized. And this principle is very popularly used in large industries where a huge amount of or huge scale production of demineralized water is required. So this is the types laboratory commercial automated. This is the laboratory column we have. This is the column commercial mode which is available in the market, and this is the automated one. This is the instrumentation, and it is very high cost. So this is the traditional one, and this is the commercial columns are available in the market, and this is the instrument one, that is automated one. So what is the principle? Now, it relies on the attraction between oppositely charged stationary phase known as the ion exchanger and analyte. The ion exchanger consists of an inert support medium coupled covalently to positive, that is known as the anion exchanger, or negative cation exchanger functional groups. To these covalently bound functional groups, the oppositely charged ions are bounded, which will be exchanged with like charged ions in the sample having charge magnitude more than the ions bound to the matrix. Thus, if anion exchange chromatography is performed, negatively charged sample component will interact with the stationary phase, that is the positive charge, and will be exchanged for like charge ion already bound to the matrix. So here there are two type of exchangers. That is, if your ion exchanger will consist of covalently positively charged, then it may be treated as the anion exchanger, and it is negatively charged, treated as the cation exchanger. And generally, your stationary phase is a positive charge, that is also the known as the anion exchanger. And this is the working principle we have. That is, consider a column having the negative ion and positive ion E minus and Y plus cation exchanger, in which E minus is a negative charge exchanger and Y plus is the mobile counter ion. So it is the counter ion or a component we have, and E minus is the exchanger. Then what happened? And another X plus with the cation in the sample having charge greater than Y plus. Then what happened? The X plus ion can exchange site with the counter ion Y plus with satisfying the following relationship. That means the column which are the cation exchange composition E minus Y plus, and this X plus is present in the sample having higher positive charge. Then what happen? Now the anion part will attach to this X plus, and Y plus gets detached. So the desired bound cation X plus can now be eluted by either two ways: by adding a component M plus having magnitude of charge more than that of X plus, so that M plus will replace X plus and X plus will be eluting out, or by changing the pH of the solvent, that is mobile phase, so that X plus have no charge and is then unbounded from the matrix and can be eluted out. So when the in the cation exchanger, the Y plus is now replaced by X plus having more positive ion, positive charge. Then this after this formation of this type of complex, the X plus can be eluted out by two ways. How? If I just exchange this complex with M plus, that is more positive ion charge than X plus, then X plus can be eluted out. Or another way is there, if I change the pH depending on the mobile and the stationary phase of the solvent, that is the pH of the solvent. If it is changed, then accordingly your X plus can be emitted out. So in this way, your component X plus from the sample can be emitted out using ion exchange chromatography, where the ion present in your sample in terms of X plus can be exchanged with Y plus, and then after formation of this complex, the complex, it is again treated with M plus, where M plus having the higher magnitude of charge. So in that case, X plus will be eluted out, and you will get the X plus ion as one component of the mixture. And this is how the working can be done in cation exchange chromatography. Just here you see, this is the resin we have, or this is known as the exchanger, where E minus is the inside, there is E minus, and Y plus are the outside. So this is known as the negatively charged exchanger or cation exchanger. So here, when X plus component from the sample it interacted, and X plus having the higher positive charge than the Y plus, then the Y plus gets out and X plus go in. So X plus go in, and we will get the X plus that are surrounding to the E minus. Then in this condition, when another ion M plus, which is having higher affinity of uh, negative charge, and it is higher positive charge than X plus, then what happens? This X plus gets out, and we will get that X plus as one of the component of the sample. Then there are four basic steps of ion exchange chromatography, that is equilibration, sample application and wash, illusion, and regeneration. So this is the first step, that is your ion exchange chromatography equilibration, where the first step is the equilibration of the stationary phase to the desired start condition. When equilibrium is reached, all stationary phase charge groups are associated with exchangeable counterions, such as chloride or sodium, are shown by the blue or red ions. So blue is the counterion, and the plus is the red ion, that is the stationary phase charge group. So there are two ions, positive ion and negative ion. So then when the sample come, this is the sample we have, then the second step is sample application and wash. The goal in the step is to bind the target molecule and wash out the unbound molecule. So these negative charges is left out with no sample is provided to them. So that's how these negative charges are washed out, and the sample buffer should have the same pH and ionic strength as the starting buffer in order to bind all appropriate charge proteins. So here buffer solution is used to control the pH, because buffer solution is a solution which pH doesn't change after addition of small amount of acid, base or water to it. So our human blood inside the body is a good example of buffer, where the small changes in acidic, basic or any aqueous changes inside the body don't hamper the internal parts or the nervous system, or you can say the blood. So that is the hematology doesn't hamper, and it is due to the buffer nature of the blood, which doesn't allow a sudden change in pH after addition of small amount of acid, water or base to it. So here in French buffer solution, the molecules are allowed to bind to the target ions, and the remaining ions base wash out. So this is the second stage, that is sample application and wash. And this is the illusion we have. That's third step, illusion. Biomolecules are released from the ion exchange by a change in the buffer composition. Now the composition of buffer is changed. So in that condition, what happened? The molecule now detached or released from the ions of the exchanger. A common way is to increase the ionic strength with sodium chloride or another simple salt in order to preserve the bound protein. Proteins are preserved relative to the number of charge group on their surface. So this is the way. So by addition of sodium chloride to common salt, your ions gets detached or released from the ion exchanger. So this step is known as illusion. That is the components from the molecule gets separated on the basis of their attachment to the ion exchanger, maybe cation or anion. So this is the separation of amino acid by ion exchange chromatography, and we have different amino acids that are released or separated on the basis of the amino acid mixture. So this is the instrumentation of the we have the different parts of ion exchange chromatography. First one is the column. So the column is made up of either glass, stainless steel, or polymer. Then packing of the column. So a wet packing method, like a slurry is prepared of the eluent with the stationary phase powder and then carefully poured into the column. Care must be taken to avoid air bubbles. So slurry is prepared with the eluent, and generally the silica gel or the ammonia is also used in this case. So application of the sample after packing, sample is added to top of the stationary phase using syringe or pipette like our column chromatography. Then the thin layer is usually topped with a small layer of sand or with cotton or glass wool to protect the shape of the organic layer and the velocity of new added eluent. So eluent means it is the solvent. Okay. So here, as our like our column chromatography, the top and bottom part of the column, it is now protected with cotton or sand or glass wool, and accordingly the eluent or the solvent is added. The mobile phase, it may be acid, alkali, or buffer. So acid, alkali means these are bases, and buffer solution may be used depending on the pH at which the process is going on. The stationary phase, anionic compound consists of cationic species M plus and anionic species B minus, and this is the stationary phase we have. The both the positive and negative ions are there in the stationary phase. Then the elution part, the components of mixture separate and move down the column at different rates depending upon the affinity of the ion for ion exchange. This is very important, affinity. So depending upon the affinity towards the stationary phase, the different components get separated, and accordingly their partition coefficient or the tension factor is calculated. The eluates are collected at different stages. So analysis of the eluate by spectrophotometry, flame photometry, polarography, or conductometry. So these are the analysis of these photography methods are very much connected to the ion exchange chromatography, and it makes a very sophisticated instrument, and it becomes very automatic mechanism for ion exchange. Then we have this the low salt illusion. Just see here, sample mixture chromatography column. So this is the column we have, and through this part your sample, then your solvent gets inside the column. So this is a knob we have. So this knob is very carefully open, and gradually when the solvent is passed through that sample, different components uh, are separated based on their retention factor or partition coefficient. So, like this sample contain three components. That is red component, it is a dark blue and blue component. And first, the red component is now separated, followed by this is the solvent part. So, this is the solvent part we have. Then the dark blue. Then we have the solvent part again. Then we have the sample part. So accordingly, depending upon the interaction of these components with the stationary phase, your components gets separated. So what are the different factors that affect the ion exchange separation? So we have the ion exchange regime we have, which is used at the stationary phase, and also we have the nature of exchanging ions. For example, in the first in the resin part, the swelling factor and cross linking is important because for the effective separation, the cross linking should be controlled as it affects the exchanger capacity. Swelling helps in proper exposure of charged functional groups for exchange of ion. So swell-less means separation of ion of different sizes is critical. So if the in ionization resin there is swelling in a faster rate, that means the separation will be done very easily. And nature of exchanging ion, we have different factors under this. That is valency of ions, whether it is monovalent, divalent, trivalent, tetravalent, or multivalent. Then we have size of ions, whether it is small size or big size. So depending upon the size of ion, the small size ions can be passed through that column very easily and get separated fast. And this is also one application of a size exclusion chromatography, which we will discuss in the uh, latter part of today's discussion. Then the polarizability, this is very important because the polar molecules gets separated um, by this method very easily. So where there is no polarity or we have the polarizability factor is there, where by which we can induce polarity in a non-polar molecule using the London force, Kisson force, Van der Waals forces, etc. In concentration of the solution. So whether the concentration is very high or low, so it also uh, make your separation very fast or delay. Then concentration and charge of ions. Then number C, it is the pH of the mobile phase because in acidic, basic or buffer phase, your separation is made depends on the type of component you are trying to separate from the mixture. Then it is the ionic strength. So as ions are involved in this chromatographic separation, so ion exchange or ionic strength of different ions is very a big factor for this separation. Then we have the mobile phase modifiers are there, where mobile phase is sometimes it is modified using different solvents. Then the last factor is the temperature factor. Sorry, this is not the last. The temperature factor is there. The last is the buffer solution. That is the use of buffer is to resist the pH after addition of small acid or alkali or water to it. So the principal aim of addition of buffer to the solution is to resist the pH. Okay, so I just read out the pH of the buffer solution should impact the same charge to the sample ion as the present in the column. Anion exchange chromatography should be carried out with cationic buffer and vice versa. So this is just the opposite one. So this cationic buffer means it is the basic buffer, and the anionic buffer means it is the acidic buffer. Okay. With buffer ion will indulge in ion exchange. It will be of no use. So these are the some factors which are affecting your chromatography technique. So the ion exchanger part, the it is the what is known as the a spinal cord of the ion exchange chromatography. So this is the ion exchangers, which on which the ion exchange chromatography stands. There are three classes of ion exchanger. One is the resin, which is already discussed. That ion exchange resins are used for the separation of small molecules, or it may be gels. So ion exchange gels are also can be used for the separation of large molecules like protein and nucleic acid, or inorganic exchangers. So separation involving a harsh chemical condition, very high temperature, high radiation level, strong basic solution or powerful oxidizing agent employ inorganic ion exchange. So depending on the type of component or molecule which you are trying to separate, the ion exchanger accordingly used. If you have a small molecule, then resin is sufficient. If you have a relatively large molecule like protein or nucleic acid, then the separation may be done with the help of gels and some gels. And if you have a adverse condition like high temperature, radiation, basic solution, powerful oxidizing agent, then inorganic ion exchanger may be used. So classification of ion exchange resin. So ion exchange resin may be of many types. So like our strongly acidic cationic exchanger. So these are made up of sulfonic acid groups. Sulfonic acid means the groups which contain or the molecule which contain SO3H functional group. These are known as sulfonic acid group. Attached to styrene, styrene is your benzene ring contain CH double bond CH2. Sorry, CH triple bond CH. Styrene. Yes, yes, I am right. CH double bond CH2. Yes. So this is styrene. Then we may have divinyl benzene polymer where two phenyl groups are present in a benzene. Then in weakly acidic cation, we have carboxylic acid group attached to acrylic and divinyl benzene copolymers. Then a strongly basic anion exchanger. These are made of quaternary ammonium salt of styrene and divinyl benzene copolymer. And under weakly basic anion exchanger, we have polyalkyl amine groups attached to styrene and divinyl benzene copolymers. So there are four types of ion exchanger resins: strongly acidic, weakly acidic, strongly basic, and weakly basic. If it is strongly acidic, then sulfonic acid. If it is weakly acidic, carboxylic acid. If it is strongly basic, ammonium salt, quaternary ammonium salt. If it is weakly basic, then it may be polymer alkyl amine groups. Then according to the source, the resin may be of different types. If the source is natural, then it will be treated as a natural resin. And under cation, we have zeolites of clay, and under anion, we have dolomites. Then synthetic resin, it will be of two types, inorganic and organic. And under organic resin, we have some polymeric resin matrices are also there. So these are the manufacturing materials by which the resin of our desired separation may be manufactured. So resins are amorphous particles of organic materials. Polystyrene resins for ion exchange are made by co-polymerization of styrene and divinyl benzene. So divinyl benzene content is varied from 1 to 16% to increase the extent of cross-linking. Benzene groups are modified to produce cation exchange resin and anion exchange resin. Resin made from both of these materials differ in their flow properties, ion accessibility, and chemical and mechanical stability. Selection of one or the other type of resin is done on the basis of compounds being separated. So this is our polystyrene resin, where different percentage of divinyl benzene content is there, and accordingly their properties as well as the working is there. Then after divinyl resin, after your polystyrene resin, we have the polystyrene resin example. This is the styrene we have. This is the divinyl benzene, where benzene is connected to vinyl groups, that is CH double bond CH2. Then this is the vinyl group we have. So when styrene is attached to your, this is the styrene, this is the divinyl benzene. When they are connected, we have a polymer cross-linked type polymer we have made, and this molecule are generally used for your resin preparation. So polystyrene resins are prepared from polymerization reaction of styrene and divinyl benzene. Higher concentration of divinyl benzene produces higher cross linkage. If divinyl benzene concentration is more, then linkage will be more, higher cross linkage. And polystyrene resins are very useful for separating small molecular weight compound, however unsatisfactory for the separation of macromolecules. Then after your styrene and uh, for divinyl benzene, your resin, we have the ion exchange gels. So the ion exchange gels are made up of cellulose or dextran ion exchanger, which are polymer of sugar glucose, possesses larger pore size and lower charge densities. Because they are more softer than polystyrene resin, dextran and its relatives are called gels. Okay. So in ion exchange gels, we have two materials, that is cellulose and dextran. So as we know, the cellulose, this is the polymer of your glucose or sugar, which is having higher pore size and lower charge density, because they are much softer than the polystyrene resin, which we have already discussed in the previous slide. So these are called gels. Then this is a cellulose structure, where we have we have the polymerization of glucose molecules, and cellulose is the higher molecular weight compound, which can be readily obtained in a high pure state. Cellulose has much greater permeability to macromolecules, because smaller molecules can be separated easily by using this ions. So after that we have the exchange medium. So we have two exchange medium, as we know, that cation exchanger and anion exchanger. The choice of ion exchanger depends upon the stability, molecular weight, and strength of the sample component. The volume of exchanger used for separation is usually 2.5 fold greater than the exchange with the ion in the sample. The ion exchanger are packed in column having suitable buffer, and it is an anion exchanger. The type of ion exchanger which is to be used depends on the type of component you are trying to separate. Okay, so accordingly you may select the exchanger. Then is the first type, that is anion exchanger. where we have the positively charged exchanger, negatively charged mobile counter ion available for exchange. So in anion exchanger, we have the positive part and the anions are exchanged. Okay, if the basic functional groups are introduced, then resin becomes anion exchanger. The tertiary amine strong anion exchanger. Secondary amine weak anion exchanger. So tertiary amine as this may donate the lone pair of electron of the nitrogen. That means tertiary amines are highly positive plus I effect. So these are strong ion exchanger. Where secondary amine where relatively less plus I effect is there in the effect. So these are your weak anion exchanger. So just here see. So the anion exchanger consists of positively charged exchangers and the negative ion gets exchanged or gets interacted with the positive ion present inside the exchanger. This is the cation, this is the reverse of the anion. Here the negative ions are there, that is sulfite ions, SO3 minus. And here Na plus ion from the sample gets attached or gets attracted or gets interacted with the negative charge of the negative ions present in the cation exchange. So cation exchanger means positive ion gets exchanged. Anion exchanger means anion ions from the outside source get exchanged. So the cation exchanger have a negatively charged exchanger with positively charged mobile counter ion available for exchange. If acidic functional groups are introduced, then the resin becomes cation exchanger. And here then there is the acidic, that is sulfonic acid, it is strong cationic exchanger, and the carboxylic acid, which is treated as the weak cation exchanger. And here SO3 minus the negatively charged exchanger, and Na plus is the mobile counter ion. Then accordingly the ion exchange agent, that is the cation ion exchange agent, is there. So these are some examples of cation and anion exchanger. In a strong anion exchanger, we have PAM, that is trimethyl amino ethyl. The formula is this one. This is very strong. The three methyl groups are here, and this is trimethyl amino ethyl. This is a also a strong, that is TPAE. Under weak anion exchanger, we have amino ethyl and diethyl amino ethyl. Where two ethyl groups are here. Under strong cation, we have sulfur, that is sulfonic acid, we may say, or if they under coordination chemistry, it may be written as the ligand sulfur. It is your sulfomethyl. And under your weak cation exchanger, we have carboxymethyl, that is CH2COO minus, or in short, it may be written as CM. So these are some examples of your anion and cation exchange. Then what is the advantages of this chromatography? It is cost effective because the your column preparation as well as the materials which are needed for that ion exchanger is very cheap. This can be reusable after thorough washing. It is easily collectible because it is as it is non-hazardous and not harmful, so widely available in the market. Then low maintenance cost is there. Then this is also an efficient technique because of its separation precision. Then also the ions may be or can be separated very quickly. And these are the application of ion exchange chromatography. The first one is softening of hard water, demineralization of water. This is very important application, and it is used in the large scale in different industries to analyze base composition of nucleic acid, to concentrate the metal ions in the sample, to measure the additives in food and drug sample, to separate protein mixtures, for extraction of enzymes from tissues, purification of solutions free from ionic impurities, separation of inorganic ions, separation of sugar, amino acid and proteins. Then the last one is ion exchange column in experience. So this is all about your analysis chromatography. So this is your unit 9. Okay. Then after that we will have the next unit, that is your side exclusion chromatography. So before that, in this chromatography, if you have any doubt or anything you wish to share, so you may unmute and you may ask your questions. DJ Lakshmi, Jitendra. So if no questions are there, we may take 5 minutes of break here, and after that we will start with the site student controller. So till then, please bear with me. Okay. So till then, please wait. Thank you, students, for your patience. So next we will move the next unit, that is unit 8, also unit 10, the size exclusion chromatography, in which the different components in a mixture or in a compound get separated based on their size. So as we know, small size particles can penetrate through a very small pore or molecular voids. So the small size particles are separated first, followed by the big size molecules. So for this part, I will also have is your presentation. So I think my presentation is now very much visible to you all. This is the presentation we have, that is size exclusion chromatography. So in this part, we have the separation based on the size, and here also the same principle, that is your partition as well as the adsorption phenomenon are applied here. So these are the content of this presentation, that is introduction followed by principle, material, instrumentation, advantage, disadvantage, then followed by application of gel electrophoresis size exclusion chromatography, and electrophoresis also one of your unit 11 I think it is. Your electrophoresis, it is I think unit 11. So membrane separation. I think last part is the electrophoresis. Yes. The last one is the electrophoresis. We will discuss it tomorrow. And this gel electrophoresis size exclusion chromatography 2, it is also your one of the content of this presentation. Then our size exclusion chromatography, that is SEC in short, it is also called gel filtration or gel permeation chromatography, that is GFC or GPC. So size exclusion chromatography, here the stationary phase is a gel. It is not that it is a resin or any solid phase. It is the gel which is used as the stationary phase. And if your mechanism is filtration, then this is known as gel filtration chromatography. Or if there is permeation is supposed to be happening, then it is gel permeation chromatography, which uses porous particles to separate molecules of different sizes, molecules of different sizes. It is generally used to separate biological molecules and to determine molecular weight of polymers. It is usually applied to large molecules or macromolecular complexes such as protein and industrial polymers. So these are the applications which are in our size exclusion chromatography. So when an aqueous solution is used to transport the sample through the column, the technique is known as gel filtration chromatography. And when an organic compound is used as mobile phase, the technique is known as gel permeation chromatography. So it is clear, when organic solvents are used as the mobile phase, then it is gel permeation. When water solution, that is aqueous solution, when it is used to transport the sample through the column, like filtration, it is known as filtration chromatography, gel filtration chromatography. And here the stationary phase is gel. The separation of molecule is called fractionation. Size of pores in beads determine the exclusion limit, what goes through the bead and what goes around the bead. So size of the pore matters for your separation of components, and also size of the bead exclude the higher dimension particles present in the sample. So this is a principle we have: a mixture of molecule dissolved in liquid, that is the mobile phase, or the solvent, which is applied to a chromatographic column, which contain a solid support in the form of microscopic sphere or beads which acts as the stationary phase. The mass of the beads within the column is often referred to as the column bed. The beads act as traps or sieves and function to filter small molecules which become temporarily trapped within the pores. So everything is very clearly written here. That is the microscopic spheres or beads are used as the stationary phase, and the sample is dissolved in the liquid phase, that is the mobile phase we have chosen, and accordingly the beads which are in the column, it is also referred to as the column bed, and the beads acts as the trap or sieves, and is function to the filter of the small molecules. Larger molecule pass around the bead are excluded. Sorry. Yes. Larger molecule pass around the bead are excluded from the beads. Larger sample molecules cannot or can only partially penetrate to the pore, whereas smaller molecule can pass almost all pores. Thus, large molecules elute first, smaller molecule elute later, while molecules that can access all the pores elute last from the column. So here, very interesting that large molecule elute first because these are not passed through that bead, small size beads. So the molecule which can access all the pores can elute at the end. Smaller molecules we can adjust it themselves within the bead are separated before the larger molecules which are not held inside the bead. Particular different sizes will elute through a stationary phase at different rates. So this is the thing, just see here, these are all beads, okay, and these beads will have some pores. So when this is the sample which is dissolved in the solvent, it is gets mixed with the beads, and when the solvent gets passed through the stationary phase, then what happen, the smaller beads gets attached to that bead, smaller particles gets attached to that beads, and the larger particles which are not the size of that bead are passed through the stationary phase and separated first. So here this is the bead we have, and the blue and the purple color, these are the sizes which are more or less accommodated within the bead size, and these red size particles are very large which cannot be accommodated to these pores. So these red size are large molecules and these are separated fast. Then these blue lines, these are the medium size molecules which is separated after the red, and the purple lines is very small. This can be held tightly with the port of the bead, and they are eluted or filtered at the end. Then total column volume Vt, it is equal to Vg plus Vi plus Vo, where Vg is the volume occupied by the packing, Vi is the volume of the solvent in the pore, and Vo is the free solvent volume that is similar to injection volume. So these are all the definitions or meaning of the each terms present in this equation. That is, Vt is the total volume of the column, Vg is the volume occupied by the packing, That means this is the volume occupied by the vacuum, the stationary phase, and volume occupied by the solvent. So when solvent is inserted, then the total volume occupied inside the stationary phase and outside the stationary phase, this is known as a VI, and VO is the free solvent volume which is injected. That means it is how much solvent is injected. It is your VO. In the component, we have the same thing: stationary phase, mobile phase, column, pump, and detector. So stationary phase, as we already know that a gel is used, and the stationary phase it is semi-permeable, porous beads with well-defined ranges of pore sizes. Beads are cross-linked polymers. Degree of cross-linking is controlled carefully to yield different pore sizes. Smaller pore sizes are used for rapid desalting of proteins or for protein purification. Intermediate pore sizes are used to separate relatively small proteins. So this is the way your stationary phase is there. That is semi-permeable porous beads with well-defined range of porous sizes are used as the stationary phase for size exclusion chromatography, and beads are cross-linked polymers. Very large pore sizes are used for purification of biological complexes. So depending on the type of your component to be separated from a sample, you should select the beads accordingly. And in market, the commercially in market, we have many stationary phases for the size exclusion or gel exclusion chromatography. We have many stationary phases are available. This include dextran, or in commercial name is Cefadex, or polyacrylamide or dextran polyacrylamide, that is cefacryl. Each this is trademark. So each is available with a variety of different ranges of pore sizes in the bead, permitting separation of macromolecules of different sizes. A good stationary phase should have the following properties. CE. So a good stationary phase should have following properties. It should be chemically inert, number one. It should be inexpensive. It should not react with component to be separated. It should not react with the element, that is the solvent. It should be colorless, uniform in size and shape. It should be mechanically stable. So these are some basic characteristics or properties a good stationary phase should have. That it must be inert, inexpensive, should not react with the any component, should not react with the solvent, should be colorless, uniform in size and shape, and is mechanically stable. Then the stationary phase, whether it is Cefadex, it is a commercial name, it is maybe soft gel, semi-rigid or highly rigid, depending on your component to be separated. So for soft gel, it is dextran, polyacrylic gel separation of protein. For semi-rigid gel, we have the biobeads, separation non-polar polymer into non-polar solvent. For this one, for non-polar, we may use semi-rigid, and for separation polar system, we may use highly rigid gel or gases. So dextran, which is one of the very commonly used stationary phase in your gel formation or gel filtration chromatography, that is the size exclusion chromatography. It is a homopolysaccharide of glucose residue. It's separate prepared with various degrees of cross-linking to control pore size. It is bought as dry beads. The beads swell when water is added. The trade name or commercial name is Cefadex. It is mainly used for separation of small peptides, and globular protein with small to average molecular masses. So this is the different important aspect of your dextran, which is also known as Cefadex, and which is a homopolysaccharide polymer of glucose, which is cross-linked to control pore sizes, and this is very useful for the separation of small peptides with average molecular mass. Then the typical separation ranges that can be achieved using Cefadex are given below. Molecules ranging from 100 to 600,000 DA can be separated depending on the type of Cefadex reservoir. So this is the reservoir containing the element. This is the mobile phase we have. This is the sample and this is the column. And depending upon the range, we may use different grades of Cefadex starting from G10 to G200. So it is the different your size of the particle in the sample. Polyacrylamide. This is another substance which is used as the stationary phase for your size exclusion chromatography. So these gels are prepared by cross-linking acrylamide with N-methylene bis acrylamide. The pore size is determined by the degree of cross-linking. The separation property of polyacrylamide gels are mainly the same as those of dextran. They are sold as Biogel P. This is the commercial name. They are available in wide range of pore sizes. So this is also another molecule which is used as the stationary phase for your size exclusion chromatography, different pore size or bead size. In agarose, this is another material for our stationary phase. This is linear polymer of D-galactose and 3,6-anhydro-1-galactose. It forms a gel that is held together with hydrogen bonds. It is dissolved in boiling water and forms a gel when it is cold. The concentration of the material in the gel determines the pore size. The pores of agarose gel are much larger than those of Cefadex or Biogel P. It's useful for analysis or separation of larger globular protein or long linear molecules such as K. So this is how your agarose component of the stationary phase works. With the different hydrogen bonding is there and with boiling water and forms a gel when it is cold and all the things are there. Then the important phase is a mobile phase. Mobile phase is the eluent or the solvent that is used for the separation of the component using the different size exclusion phenomena. The liquid used to dissolve the biomolecules to make the mobile phase is usually called as a buffer. A mixture of biomolecules dissolved in the buffer is called sample. The choice of mobile phase to be used in any separation will depend on the type of separation to be achieved and component to be separated. The most common solvent or mobile phase or eluent in for polymer that dissolve at room temperature is THF, tetrahydrofuran, chloroform, or trimethyl formamide. So these are the frequently used solvents in your size exclusion chromatography. Then we have the mobile phase and the solvent. If your material is elastomer, polybutadiene, polyisoprene, the solvent is toluene. If it is polystyrene, polyvinyl chloride, styrene butadiene rubber epoxy resin, then PHF. If it is polyolefin, trichlorobenzene. It is polyurethane, then dimethyl formamide. If it is protein or polysaccharides, then it will be water or water. Then it is the solvent selection. The solvent used for mobile phase of side exclusion chromatography are limited to those follows the following criteria. The solvent must dissolve the sample completely. The solvent has different properties with solute in the eluent, typically with the solvent refractive index. Solvent must not degrade the sample during Otherwise, the viscosity of element will gradually increase over time. The solvent is not corrosive to any component of the liquid. So these are all the solvent selection criteria which is generally obeyed during selection of solvent in for our size exclusion. Then it is the sample preparation. The sample solution are supposed to be prepared in dilute concentration, that is 2 milligram per milliliter. A good solvent can dissolve a sample in any proportion in a range of temperature. Samples with broad molecular weight distribution may require higher concentration. It is recommended to filter the sample solution before injecting into column in order to get rid of clogging and excessively high pressure problems. So this is how the sample is prepared. Very less concentrated sample is prepared. It is also a good solvent is used for the sample preparation at normal temperature. So samples with broad molecular weight distribution may require higher concentration. It is recommended to filter the sample solution before injecting into column in order to get rid of clogging and excessively high pressure problems. Agitation and filtration. Generally, filtration is required to remove insoluble impurities. So, agitation and filtration both are required, but the filtration is generally used to separate out the undissolved particles from the solution. Do not agitate and filter samples that contain very high molecular weight, that is greater than 1 milligram. And after the molecular sample preparation, we have the column preparation. So in size exclusion chromatography, the commercial available column, it is known as analyte column, that is 7.8 to 8 milliliter in dia. Preparative column, that is 25 to 25 mm in dia. Then usual column length is maybe 25, 30, 50 and 60 centimeter of length. Recently narrow bore columns 2 to 3 millimeter dia may have been introduced, which save time and solve the problem of delayed separation of components of a mixture of a solution. Selecting SCC column, it may be shorter column, save time and solvent. Small particles provide a better resolution. On the other hand, 5 millimeter packing are more sensitive towards contamination by samples containing impurities. Particles as large as 20 millimeter have been recommended for very high molecular weight polymer. So this is our selecting a SCC column. It should be, the column should be short to save time and solvent as well. Smaller particles are provided for a better resolution, and the packaging must be sensitive. So small size particle packaging can sometimes result in shear degradation of large polymer molecules because the space between particles is very narrow. Column with different porosity or mixed bed column provide a better separation. So these are the some characteristics points of a column to be prepared with different pore sizes with using the beads. So how size exclusion chromatography column is handled? So this is handling of SCC column. A column set in SCC should be always run in the same mobile page, that is isotropic. SCC column should never be operated in a backward direction. Yes, it should be from it is from the top to bottom, that is your descending one. Care should be taken in connecting column or in sample injection. Replacing a clogged inlet thread is a dangerous operation which can reduce column performance. A damaged or dirty check valve or pump can also be reduced column life. So all should be carefully handled and checked before going through the SEC separation. And this is just a SEC uh, your chromatography where we have the mobile phase here. It is the injection valve and it is the pump. I just laid out the different parts. It is the column we have, and this is the loop, detector interface, and data station here. So here what happened? The column is prepared, and with the help of this injection valve, the sample is injected here. The sample is now injected, and your your solvent, your solvent that is also injected through this pipe, and it is now connected here, and the solvent gets passed through this column, and accordingly on the basis of their bead size as well as the uh, higher size, the larger size particles, the particles get separated and it is detected by this detector, and your peak on the spectrum, your SCC chromatography spectrum is detected here. Then a pump is there, used as the series pump or reciprocating pump. So a highly constant flow rate has to be maintained during the entire chromatogram. This is very important in HCC. A change of the flow rate of only 0.1% can cause an error in molar mass of up to 10%. Most pumps can only reproduce the flow rate to 0.2 to 0.3%. A line filter in the solvent reservoir may prevent particles from coming into the pump head, which might damage the check valve or the pump seal. So different type of pumps used are series pump and reciprocating pumps. Reciprocating pumps. There is a detector which detects the different components with different electrical signals. So we have many detector types like bulk property detector, refractive index detector (RI). For our solute property detector, it is UV detector, and for evaporative detector, it is evaporative light scattering detector (ELSD). Evaporative light scattering detector. Then molar mass sensitive detector, it is light scattering detector or low angle light scattering detector or multi angle light scattering detector. So we have many type of detectors which are used in our size exclusion chromatography. Then we have also viscosity detector for differential viscometer, and other detectors may be used are FID, that is flame ionization detector, mass spectrometer, or a Fourier transform infrared spectrometer, which is also known as FTIR. What is the advantages of this separation technique? Like it is short analysis time, well-defined separation, narrow bands and good sensitivity, no sample loss, small amount of mobile phase required, flow rate can be set. What are the disadvantages? Limited number of peaks that can be resolved within the short time scale of the gas formation, gel formation chromatography run. Filtration must be performed before using the instrument to prevent dust and other particulates from running the column and interfering with the detector. The molecular masses of the most of the chains will be too close for the GPC separation to show anything more than broad peaks. And these are the applications of our gel formation chromatography or size exclusion chromatography or gel filtration chromatography. The applications are protein fractionation, purification, molecular weight determination, separation of sugar, protein, peptides, robbers and other on the basis of their size. This technique can be determined the quaternary structure of unified proteins. Let's try to remember. And side exclusion chromatography is a widely used technique for the purification and analysis of synthetic and biological polymer such as protein, polysaccharide, and nucleic acid. Various species of ribonucleic acid and viruses have been purified using agarose gel. It is also used for desalting and for co-polymerization studies. So this is all about your size exclusion chromatography. So in this part we have already covered out all the things in that PowerPoint presentation. Okay, so these are the beads which are used of different used as the stationary phase, and this is the sample which is soluble in the solvent. It is mixed inside the column. Then the big size particles which do not get fixed or entrapped to the pore of the beads. These are separated fast, followed by the small size particles. In different chemical equations are there. Matrix should be inert, chemically stable, low content of ion, availability of white phase of gel, availability of gel with different particle size, mechanical rigidity of the gel particle. Then come the dextran, Cefadex, dextran that is cefacryl, polyacrylamide gel, agar-agarose, and styrene diethylene butane. All the things are discussed in our PowerPoint presentation. So this is the uh, Cefadex molecule we have. Dextran, Cefadex is the commercial name, and this is how your cefacryl is shown here, where your dextran with the N-index methylene bis-acrylamide gets interacted. Then polyacrylamide gel, where one amide group is there, that is double C double bond or NH2 group is there, amide group. Then we have our agarose gel, where galactose or D-galactose or N-galactose residue are used for this gel preparation. Styrene vinyl already discussed. The unique feature of this technique, some applications. Under application, we have analytical group separation, analytical fractionation, measurement of protein binding and complex formation, determination of molecular weight using the Cefadex grade G100 and G200, also biogel P. Then preparative application, group separation is there, preparative fractionation, miscellaneous application. Then the summary part of the species will come. Okay, so this is all about today's discussion. If you have any queries or any point to share or anything to ask, you are now welcome. That is Jitender or Vijay. The attendance is very poor, and also yesterday I have shared the two, sorry, the PowerPoint presentation of planar chromatography, and today I am sharing the two parts that are discussed. Okay, that is side exclusion chromatography and ion exchange chromatography. So just wait, student. I am sharing the PowerPoint presentation with you for better understanding. And so, anyone, uh, please share your experience. What is the how is the class is going? How what is the level of understanding you have, or anything remain remain in doubt, or anything you wish to share, or to ask question? You are very much open. And you, in this part, you just remember the type of stationary page and the solid page, sorry, stationary and the mobile page, which are used in different chromatographic methods. And depending on the type of mechanism that is involved, accordingly the chromatogram or chromatography name, that it may be liquid solid chromatography or liquid chromatography. If the stationary phase is solid, it is liquid solid. If stationary phase is liquid, it is liquid liquid. And if it is your gas chromatography, it may be your planar chromatography, it may be your paper chromatography, thin chromatography, and today we discuss the ionisation chromatography followed by side exclusion chromatography. So all these chromatography mechanisms are very much used in detection of simple in detection of different components of a mixture. So you are suggested to read out all the things EGDS. This is the side exclusion chromatography and the ionisation chromatography. So Jitendra and Vijayalakshmi, your PowerPoint presentation is shared in your WhatsApp group. So you are instructed to go through that PowerPoint presentation very carefully, and these are very precisely and briefly written, and try to remember the important aspect of both the and chromatography as well as the side studio chromatography. Just
Okay, sir.
so Jitendra, am I audible?
Yes, sir.
सो अभी हमने जो 5 दिन में डिस्कशन किए हैं ओवरऑल कुछ कुछ बात आपका समझ में आ गया या नहीं?
अ, कुछ तो मुझे आया, कुछ तो मैंने जैसे प्रैक्टिकल किए हुए थे ना कंपनी में।
ओके ओके ओके, तो
तो
बस इसमें जो है क्रोमाटोग्राफी में आपको बस याद रखना है कौन से क्रोमाटोग्राफी में क्या स्टेशनरी फेज यूज हो रहा है, क्या मोबाइल फेज यूज हो रहा है. सो स्टेशनरी फेज और मोबाइल फेज को लेके उसका मैकेनिज्म जो होता है उसको अकॉर्डिंगली हम डिफाइन करेंगे. अगर सॉलिड फेज अगर स्टेशनरी फेज है वो हो जाएगा आपका एडजॉर्प्शन। इफ द स्टेशनरी फेज इज लिक्विड द मैकेनिज्म होगा क्या ना पार्टीशन। Then accordingly, your in paper chromatography, a paper is used. It will be ascending or descending. If it is a thin layer chromatography, a thin layer plate is used. If it is a column chromatography, a column is used. If it is a your liquid chromatography, the stationary phase is liquid, and your um, mobile phase is also liquid. So in liquid stationary phase, if your supporting medium is there, it may be your silica gel or it may be your alumina or your charcoal powder also. So in gas chromatography, the gas phase treated as the mobile phase and the solid or liquid treated as the stationary phase. Then accordingly, today we have the ion exchange where ion exchangers are there. If it is anionic ion exchanger, it may replace the cation. If it is a cationic exchanger, it may replace the anion. And in your Jitendra, you are not in that WhatsApp group.
नहीं सर, मैं हूँ ग्रुप में।
ठीक है, तो हमने तो उसमें आपका ये कर दिया, आपको शेयर कर दिया जो भी मेरा था, आपका जो पावर पॉइंट प्रेजेंटेशन था मैंने दे दिया उसको।
वो विजय लक्ष्मी ऐड नहीं थी ना, तो उसके लिए शेयर किया था मैंने। तो इसमें से हम दो ही, मैं और चैतन्य ही हैं, और कुछ कोई है नहीं ग्रुप में।
तो ठीक है, ये जो भी हमने आपको शेयर किया है ग्रुप में, आप वो पावर पॉइंट प्रेजेंटेशन को फॉलो कीजिए और अकॉर्डिंगली आप अपना जो भी नोट्स बनाना है या उसको पढ़ के याद करना है आप अकॉर्डिंगली उसको करिए, ठीक है। और आज
सर इसके
हाँ बोलिए।
जो असाइनमेंट बनाए हैं वो मुझे दिल्ली जमा करने हैं या फिर भुवनेश्वर?
ये आपका रीजनल सेंटर क्या है, कौन है?
मेरा रीजनल सेंटर दिल्ली है।
तो आपको दिल्ली में करना है।
ठीक।
तो आपका ये जो क्लास हो रहा है ये ऑल ओवर इंडिया का क्लास है, ठीक है, सेंट्रलाइज्ड क्लास होता है हर प्रोग्राम का। तो जैसे इस सीजन में और इस सेशन में भुवनेश्वर को मिला है पीजीबीएससी का क्लास करने के लिए। तो अभी दिसंबर सेशन में पटना को मिल सकता है, दिल्ली को मिल सकता है, अहमदाबाद को मिल सकता है, ठीक है। तो ये मतलब इन रोटेशन बेसिस ये हर प्रोग्राम हर आरसी को दिया जाता है। तो
ओके सर।
आपका ये जो है पीजीडीएस का इस बार ये भुवनेश्वर कंडक्ट कर रहा है। तो इससे पहले मैं भी क्लास लिया था लेकिन वो शायद 1 साल पहले या 1.5 साल पहले था, अभी आपका पीजीडीएस का कोर्स जो था
जी।
तो लेकिन हमारा जो भुवनेश्वर सेंटर है यहाँ पे साइंस का बहुत सारा प्रोग्राम का ऑनलाइन क्लास होता है, जिसमें मोस्ट ऑफ द केमिस्ट्री और एनवायरमेंटल साइंस में मेरा तो क्लास रहता ही है, मेरा जो भी टीचर लोग हैं उनका उनका भी क्लास रहता है। तो ओवरऑली आप ये पीजीडीएससी का जो पीडीएफ सब है तो आपके पास अभी?
जी सर।
ठीक है, तो अभी असाइनमेंट आप सबमिट करो, करने के बाद आपको दिसंबर में जो भी आपका एग्जाम है उसको अटेंड करिए और जो भी प्रैक्टिकल रिलेटेड जो भी रहेगा आपको मेल में कम्युनिकेट किया जाएगा, ठीक है।
जी सर।
चलो, तो अभी क्लास को यहीं पे हम एंड करते हैं और tomorrow is the last class and if you have any friend or anybody just intimate them to attend that class because tomorrow I will discuss all the units from 1 to 12 in a brief manner and if any doubt or anything you wish to share you may contact tomorrow, okay?
जी सर।
So, chalo. Thank you to all for your patience hearing on behalf of Regional Central Group Bhubaneswar. I thank you all for your patience hearing and hopefully our last class will be a thrilling one where we will discuss all the separation techniques very briefly and I hope there will be no doubt within you students and let's wind up the class and tomorrow we will meet again. So thank you.
थैंक यू सर।